Okay, so yeah, so this is going to go through start fairly high level, and then we're going to deep dive into quite low level. So Blackwell fundamentally is about serving. It's about inference. Most of the things done are all on that side. And whilst there are some improvements that help for training, and many of these improvements help that side, it's really all focused on. There's virtually nothing specifically for the training side. It's all about serving. Ah, where did that just go? Oh, okay. Does it still appear all right on your side? It just suddenly changed on me.
It does.
Okay. The screen suddenly changed and I don't know what happened. Okay, so oh, it is that. So yeah, there's kind of four main improvements. The first is that they radically changed the memory structure. They added things like tensor memory, the TMA improved, they decreased the L2s, they increased the HBM sizes, and did a few things to just generally to try and improve the concurrency. They also really brought the low precision stuff first class. FP4 and their custom versions are like all the way through the tensor cores, so they really want to use that. It's going to later. The other thing that is they actually, Blackwell isn't a family, it's two. They changed the sort of data center ones, the B series, are quite different from the consumer Blackwells, which is the RTX Pro and GeForces. So there's two very distinct things. Now, obviously, we'll mostly be concentrating on the big boys, the data center ones, but it's worth noting there are differences, and I will mention it. And another thing that, again, isn't something we're going to focus on, but they spent quite a lot of work bringing the scale up. NVL 72, which is their rack level stuff, which involves new NV links, involves quite a lot of things to support really big 72 GPU. So we won't cover it much, but it's worth knowing they did quite a lot of work there as well. So the first thing is just to get over this fact that there are two families. They're actually fit into four SKUs, really. There's the original, or the main Blackwell, if you will. That's the B200 and the GB200s, and that's compute capacity 10. So that's main thing in terms of sort of inference and training is it includes 180 or 192 gigabytes of HBM. It's got the NVLink 5, and it's the main, has most of the tensor core stuff that is Blackwell. They've then spun out a refresh. If you remember back to Intel's day, they used to have a tick and a top. So Blackwell Ultra would be the top. It's got small amount of improvements, but so it's not a complete architectural change, but it's got a number of improvements, and that's the 300s, and they have a compute capacity of 10.3. One of the big things for actual serving is they have a lot more RAM, HBM RAM, and they have a few things to help the inference. The prime one being they have faster FP4. So they've kind of pushed that more. And then on the other side, you've got the desktops, and that's split into two families. You've got the RTXs, the standard graphics cards reaching up to the 5090, the consumer end, and you've got their professional family that go up to the 6000. The 5090 is the largest consumer one with 32 gig. The RTX Pro 6000 is the biggest of that line at 96 gigabytes. But they're principally at GDR7. So while they've got a lot of bandwidth, it's still nowhere near the HBM. And they're also designed to be plugged in via PCI Express. So they don't have any fast multi-card stuff all goes over it. And they actually use what's called compute capacity 12. And that's because they don't have tensor cores. And then the kind of odd one is GB10. That's the only part of that family so far, which is kind of, it doesn't really have a thing. It's somewhere in between. So it's got a Blackwell chip, but it also has, but it uses slow RAM. In fact, it uses LPDDR5, which is the low power version, the stuff that's in mobile. But it has a lot of it. It has 128 gigabytes, and but really slow RAM, only a couple of hundred gigabytes per second compared to the GDR7 on the consumers, and even nowhere near what the HBM can do. So it's designed very much as sort of a mini but super chip computer. So the other thing to note is some of these parts will have a G in front of them, so GB10, GB200, and that refers to Grace, which is NVIDIA's CPU structure. So on the GB10, it's got like 20 ARM cores built in. It's not a PC, it's a dedicated box. And with the data center ones, the GB200 and GB300, they have a set of Grace CPUs connected directly. So they're like complete supercomputers. So in terms of what we really care about, we're going to look deeper here. So the 5th gen Tensor Core is the really big feature. And it's worth knowing it is only on the data center ones. So none of the others have these. They continue to use Hopper, a basic, not basic, but Tensor Core 4th gen, you call it, which is via WGM MMA instructions. Whereas Blackwell, proper Blackwell, data center Blackwell, has a complete separate set of instructions called TCN Gen 05. And the key thing about those is they support, they're much more designed for inference, and they support a lot more quantization formats at the hardware level. The other big thing about TCN Gen 05 that is tensor memory. So Blackwell have a separate 256 kilobytes of SRAM, static RAM, that is just for the tensor unit. And this is designed to store intermediate tensor results, the matrix multiplies. So they essentially have a dedicated storage for the tiles. As I mentioned, the HBM tech has been being upgraded. So they now get a total across the whole rack. You can get 13.4 gig on a GB200, and a 300 pushes that to 20 terabytes. And it has huge bandwidth. And as I say, but the NVLinks were also upgraded, which for small scale gives you about 1.8 terabytes a second per GPU. And if you have this huge rack, you can get ridiculous amounts of bandwidth across all the 72 GPUs. Smaller things that are not headline, that are kind of just there, are the fact that the Blackwell increased the level 2 cache by quite a bit. It's now 126 megabytes. They also have a few tweaks to the thread block clusters and the whole cooperative arrays. How important that is, it's hard to tell at the moment. There's not much information, but they've certainly tweaked it to make it be a little bit better. And they also have the decompression engines. So this is for the really big stuff that they can actually, when they read stuff directly off the SSD disks, the NVMe disks, they can do hardware decompression of a bunch of the standard compression formats, which helps when you're doing really, really big data processing. I don't think it's very useful for just the straightforward sort of normal inference, because we want all our weights in memory. But if you are actually over your amount of VRAM, then that could be really useful. And as of course, they've improved the CUDA stack, as you would expect, with all the new compilers and some new ideas like CUDA Tile, which is a new, just hit C++. It's in Python as well, which is a way of the compiler doing the tiling for you. So you kind of automated tile sizing. So in terms of what we as kernel writers will be thinking about, we go from VRAM, a traditional, which is HBM for the big data centers. You then use the TMA to move stuff into S memory or T memory. Then you use MMA, which is the matrix multiply accumulator instruction. It does all the work, sending the results back to immediate into TMEM, the accumulator, and then finally you do the epilogue out to main memory. So they've improved most parts. So as I said, the TMA essentially is a DMA unit, and now does a lot of the sort of just stuff that used to take a bit of time in the CUDA cores. Now does it for you. It can swizzle, it can transpose and things like that. The epilogue, by improving the way the Tensor Core and the CUDA cores work together, you can actually get much better overlap. And yeah, and of course they have this completely separate Tensor Core. that is a lot more separate from the CUDA cores. Whereas prior, Hopper and before, the tensor cores were still very much tied to the warps themselves. At Blackwell, they are now largely separated. It's essentially its own separate chip that just does a very, very single operation. And the TMA is essentially its own DMA engine.
Dean?
Yeah.
I think Pramod has a question.
Okay. So I've let that go.
Sorry. So how is TMA different from TMM? I thought even TMA was that it had its own basically hardware units for asynchronously moving over the data from like your global memory to shared memory. So
yeah,
what's the difference between TMA and TMM?
This is a perfect slide to describe it. So yeah, so the TMA is basically a DMA unit. It's a very fancy DMA unit, but it's a DMA unit. Its entire job is to copy data to and from HBM to either shared memory or key memory. So it just asynchronously moves data around, and as a part of its moving data around, it has a whole bunch of operations to swizzle and transpose. Being asynchronous and separate, you basically kick it off and then wait for a while. And the reason for that is that there is now there are two distinct sets of SRAM that you have to deal with Blackwell. And that is the Tensor's memory and the shared memory. And so both of them are fast, but the Tensor memory is very specific to just a certain operations. You can use it for other things, but I don't think anybody ever will. So from the sort of large scale, first of all, you have your register pool, which is 256 kilobytes per SM. And that's really fast. It's one cycle. But we have the occupancy because it's shared. You then have the tensor memory, which is another 256 kilobytes. You see this number come out a lot, which is lane routed. It's not the same structure as your normal shared memory, so that it's designed for the tensor operations explicitly, and the TSA can go directly into that if necessary. Though usually it probably goes through shared memory, but that's just the way that it's set up. You then have your shared memory, which is 228 kilobytes. If you're wondering a little thing here, the actual RTL macro is probably 256 kilobytes, but they've borrowed bits for things like write buffers, and that's why it's probably 228 and not 256, because other bits are being used for some of the others. But you have up to 228, and that's your normal CUDA shared memory that we've loved and all the other thing. But TMA can read from it and write to it, so it can choose where to go. Additionally, the CUDA cores can load stuff from register or S memory into T memory themselves, like the traditional way, though that might not always be the right way to do it. Generally, you want to use the TMA to do it. And the point about that is these are getting slightly more latency. Register, yeah, really fast. TMEM, it's actually not that fast, but because it's pipelined exactly to the tensor core, we don't really see it. It's just very fast. So we don't really get to see its speed because it's pipelined exactly to get the exact rates they get out of the tensor core. Shared memory, you have the usual thing. It's still pretty high bandwidth, but we have to think about bank orders and bank clashes and that kind of thing. And again, an additional thing, technically you can decide not to share the shared memory between the level 1 cache and the shared memory, which makes sense in some data patterns, but not really AI. So for us, you probably never want to use it. You don't want to use level 1 cache because we know the fixed order, the fixed size are almost make it easy to use shared memory, which in the old days was called scratch. The difference between scratch and L1, but so we will probably never really care about the fact that it also can be used as a level 1 cache. On top of that, you then got your level 2, as I said, they also increased. And as you can kind of see with these sizes, you get more bandwidth in each one, more latency, but they also go up in sort of a magnitude of size or a couple of order of magnitude in size. You then have your HBM. Yep, it's huge, but because the arithmetic rates have also gone up, it still feels really slow. HBM is stupidly fast, but it's just not fast enough compared to the static RAM, so it feels slow to us. And then finally, something you need to investigate, and you have the NV link fabric, which is when you're crossing across with tensor parallel stuff, which is down at 1.8 terabytes a second. Yeah, so it's kind of you could kind of each of these you're going up an order of magnitude in speed and size. Yeah. So this is a little bit on the shared memory. Just to point out, this is the first big difference you notice between the consumers and the data center ones. Data centers have 228 kilobytes of shared memory. Consumers have 128. So it means you can't even use the desktops to kind of just the shared memory bit. They don't. They're different there as well. So you can't really have the sham kernels at all. You can choose this size. Again, this is a very low level via CUDA. Probably done for you via the higher level Python libraries, but you can actually explicitly set, I want this much shared memory. 228, you have to be careful with. It is, in some ways, it seems the easiest. I want to use all of it as shared memory, but it does hit your occupancy. You can only get one CTA mode on 228. So you probably, in most cases, you want to use a little bit less and get a small CTA at the same time. It is also worth noting that the TMA descriptors and the barrier objects you need to keep everything in sync also take shared memory up. So you want to always keep a couple of K in your shared memory allocation just to cover the DMA descriptors and the actual shared objects. Yeah. Okay, so this is the TMEM shared memory. TMEM shared memory, static memory, I would say. So it is very much in matrix form. So what you actually get is a bunch of columns and 512 rows. Now, because it's sort of aligned with the usual warp size, it's not actually a warp in this conventional sense, but it's 32 columns is how much you allocate. And so you end up with, you can have 128, each of them is 512 rows, and each one is 4 bytes. And that's kind of where you allocate. It's not bank organized like S memory. It's actually in terms of parts of the matrix. So you decide how much to allocate with an instruction at the PTX level, and then that's freed when the kernel exits. So it's managed, and you decide how much. And you basically have 2 or 3 things to put in here. The first one is you always need to put your accumulator in here. So the tensor units always put their results back into T memory. And one form, they have 2 basic forms. One is they get their source A and B from the shared memory, and another form they get the B from the A from tensor memory. So essentially in here, in a sort of full fastest operation, the first time you just accumulate into it, then the second K pass over it, you would probably be accumulating back to itself. So you're putting new data in from shared memory and reusing and using this for the whole tensor core. Everything sort of comes in here and spins on here. And that's because it's designed, it's pipelined, and it's like it's essentially a dedicated, very custom unit. It doesn't have much flexibility. And that also applies at the CUDA level, because the load and store, which you can do, they can't like cross warps. You can't move from one thread to a different place. It's like every thread in the warp has a specific lane in this. So you can move stuff to it, but it's very much a whole warp right, and it goes to a certain place. It's deliberately not flexible. So one thing to note, however, is that in 2 CTA mode, you can actually effectively treat this as double, because they each have their own 256. It's fairly normal to actually try and pair these up and bring your up to 256 explain that next, I think, but that's a fairly normal form. You actually join two SMs together effectively and treat them as one big matrix multiply. And it's designed for that.
Sorry, a couple more questions. So once the matrix multiplication is done, so the accumulator has the results of the matmul in TMEM, right? So how do we write it back to global memory? Do we have to write it to registers first and then push it from registers to TMEM, or can we issue command directly to TMEM to global mem?
This is exactly what the TMA is for. So the TMA can write and read and write TMEM. So it can take the results here and send them straight out to HBM. And its big job is not going through registers. And this is why it's actually getting extra sort of simple operations added to it, not just moving. But yes, the sort of normal, if you're pipelined way, would be that you would be double buffering this. So the TMA is moving out the result to main memory, while the other part is doing the calculation in the other half. You're double buffering it. And that's explicitly the DMA is the TMA. It's still just a DMA unit, but is designed to do. It explicitly can move data in, it can move data out. Yeah.
Thanks.
So the other sort of less sort of advertised part about the memory architecture is this big increase in level 2. So because it's a memory, full memory, everything can go through it. So you can control it to a certain degree about what gets put in it and what doesn't. And you can actually have some CUDA level access to say which things are going to go in level 2 and which things are just going to pass through. It's quite a low level thing. You know, we're kind of at the real sort of optimization stage of trying to get everything out. But it's important if you can sort of do an outer tile that fits neatly into L2, you get another boost of performance. One interesting thing about this is this is the point where you can actually notice that Blackwell is 2 dies. So if you didn't know, Blackwell isn't a single GPU die. They put 2 of them and they stuck them together as glue with a really fast band between them. But it is actually there still has to cross that boundary. And so when the L2 actually gets less bandwidth for half of it because it's actually on the other die. It's a very small thing, but it's interesting to see that this actual architectural decision to enable them to have so much on the Blackwell GPUs, you can see it in the performance that you have to cross that boundary, that there are 2 dies there. And I'm probably going to say it every time here because it comes out. The whole point or a reason why they're pushing all the quantization here before is because everything gets gets smaller, which means your bandwidth goes further. Yeah. So quickly, well, not quickly, but onto the actual FP4. So FP8, of course, is the classic hopper format used by quite a lot of weights. And there are actually 2 hardware FP4 formats supported on Blackwell. The first is a kind of cross-vendor type called MX FP4. So all the vendors, AMD, NVIDIA, Google got together and decided on a bunch of quantization formats. There's a 4-bit one, there's a 6-bit one, maybe another one, maybe a 3-bit one. And they are block orientated. So every 32 values, there's a scale to decide the 4 bits, how much it works, because FP4 on its own is very, very hard to use. Possible, but it only works in certain things. However, NVIDIA came along and it looks like they found something that worked better because they really pushed for their custom one. And what's different about this is that every 16 of the FP4 values have an FP8 scale. And then there is a bigger FP32 scale for the whole lot. So basically, instead of it just being 16 4-bit values, you have 16 4-bit values, then an 8-bit value that scales all them. And then bigger up, you then have a 32-bit value that scales the whole set. So this is slightly bigger because it's more often, it's having every 16 values, not 32, compared to MX32. But it at least in their claims, it works better. And excuse me, and gets better usage because you've got more finer scale, while keeping it still very small. From a general path sort of thing, this is the kind of route, though, where MX4 FP4 and where NV FP4 actually end up. Swap probably depends on the data and so on. But yeah, so you're paying a bit more than the size for than a plain FP4 because you have to store your scales. But still, in theory, if you can get your data in that format, it's lovely and small. Their hardware ultimately eats it, so it's just, that's what you want to try and get to. That's what they've really designed it for. So now that we've got to talk about compression and the TMEM and SRAM size, we can now actually look at some typical tile sizes and how that works. So fairly obviously, FP16, 2 bytes per element in the matrix, all the way down to 0.5 for an FP4. And if you, this is not necessarily the right numbers. This is what we have to scan across and things. These are just example ones. I don't want to indicate these are right sizes. These are just trying to put some basic numbers in to show how show one possible route. So the obvious way you can, if you're using a quarter of the size data, is you increase your K by 4, go from 16 at FP4 to 64 at NVFP4. And then, you know, that then works out your size of your matrices you can have. And what you find is that you pretty much always want to use half your TMEM because of the double buffering. So you're basically trying to get the best numbers that get up to about 128K. And with these numbers, you can see that this is using the idea of this particular one where both the A part of the matrix and the B part of the matrix are in shared memory. So this is the first part, the biggest amount. You've got you've just loaded it up from your main memory. It's sitting in your shared memory, and you want to use multiple stages to keep the pipeline in. So you pretty much have around 48K, and that's where these sizes come out. So for FP8, for example, you've got 48K. That's the size of A and B. Just can't brought in from HBM. You've got enough buffers for do 4 of them that comes out to 192 kilobytes. So you're using most of your shared memory, but then you've got pretty pipelined all the way across the system. Now, the interesting thing, and probably why you start to see why they increased it to 228K, or why they use that little bit extra rather than going for the obvious power of 2, is the scales. So for both MX FP4 and NV FP4, they have to store in the S memory the scales as well. So they take a little bit more memory and just getting up to very close to the sort of maximum amount. So you can just fit with these kind of sizes. So, you know, again, you can kind of see this is kind of optimal. If you can get this, your gems are pretty much at as fast as the system can do, which is not always practical, but it's the number we want to aim for. Again, you can fiddle with the tile size a bit, but these are kind of the numbers you're looking for. As I mentioned, 2 CTA, where you combine 2 of the CTAs together, it's pretty easy because all that happens is the BM of the matrix just doubles because they actually have 2 of everything. So that's a pretty easy way of you working on a bigger matrix. And if you can do, if everything lined up nicely and you can do a 256 by 256 by 256 tile, which is kind of the optimal shape if you can do it. And that uses 2 CTAs. Yeah. So the point about this is just to show that that's the reason they're pushing the quantization so hard. It really comes into their matrix, because they don't dequant, the matrices really love it. They can just push the ALUs to the max and get the best gem numbers you can get. If we look at that a bit more, even lower level, and look at flash attention and the pre-fill side of it, what you're seeing here are it's pretty much the same stuff, but you can kind of see there are sweet spots. And for pre-fill, you can aim for this. Decode, you probably can't, and the reason is your Q is 1. So you put in your decode, if you compress everything up, and that's great, but you probably end up bandwidth limiting. And there, it's your bandwidth that matters, and it's actually KV cache bandwidth. And so this is sort of separate optimizations. If you want to, for the flash attention, we also want to be looking at using the FP4 if we can get away with the precision. But it's less important for pre-fill. slightly weird, but it may matter. So this is just another, obviously I'll send the slides and you can examine it, but you can kind of see again, there are all these numbers have been carefully picked to try and hit an optimum. NVIDIA haven't sat there and just said how fast we make it. They pick every part and say how much can we get out of this unit and what do we need to get there. And so that's why there's so much focus on the quantization hardware in Blackwell. It's all about using this memory as fast as possible, and trying to get the actual bandwidth up, because that's really what matters. So this also brings up the obvious question about how do you quantize and what do we need to quantize? The simple answer is it's complicated, and it actually depends on what part of the pipeline the quantization is occurring at. The simplest one is weight quantization done offline. There are a couple of techniques, PTQ and QAT, supported pretty much. There's a couple of classic papers. There are some new ones, so it's interesting whether or not this can be improved. And this is done offline. You take the original weights, you set a huge computer that compute power with lots and lots of cores, and it just churns away for an hour and does statistical analysis and pumps out the FP weights and the block scales for you. The only real complicated thing about that is ideally you want to produce the weights in the exact format that can be eaten up by the TMA. So in an ideal world, you do the offline to the chip you're loading. So you actually aim for a B200 or B300, because that way you can pretty much get this in the format that the TMA is going to load. Because the hardware is then decoded, it has a particular format it likes. Put the scale before it or at the end makes a difference, because it means you'd have to rearrange or load, or even potentially when you're loading it into the actual tensor core. So you pretty much just want to pick the right format that you like and hit it. So, you know, if you're using NVFP4, you would actually sit away and just whatever their hardware uses, you actually bake it out at that from the weight quantizer. But that only works for weights, right? Because activations are being updated all the time. So what they've added is the CUDA cores actually have a custom convert instruction, which it's nowhere near as good as the statistical analysis done for the offline, but then it's doing a lot less. It just has to take, for example, 16 values or 32 values and find some min scales for it. And so they have to help this and keep this fast, there's an explicit instruction for that. Ideally, you want to fuse this into the upstream ops epilogue. So it's just done as a part of finishing up when it's generated. It's like it never materializes as a non-quantized number. And then the whole point of this is that the MMA, the tensor core unit, consumes these. So effectively, it does D equals A times the scale of A, dot product B, scale of B plus C. It doesn't ever dequantize, and you really don't want to have to dequantize to get the best benefit here, because the tensor core doesn't do it. You'll be doing it in the CUDA cores. That means the TMA can't do it. So you kind of end up, you want to stay all the way, don't dequantize unless you absolutely can't do it. And then that's probably the wrong shader, right? I mean, the wrong kernel. Because that means you're off the hot path. And yeah, in terms of the actual where things are, prefill, it's all about getting that maximum out of the tensor core, using FP4 where you can get away with it, and making sure that your tensor memory unit is using TMEM properly, because in that it's huge. You just got to figure out how to get as much as possible through it. Ideal kind of, in a way, simple optimization, but it's like here we just need to use the machine hardware as good as possible. At decade stage, it's no longer about just the hardware, because it's small batches and there's launch times. So that's where things like using the graph control flow stuff in CUDA, persistent kernels, fusion, we know all this stuff. I'm just saying, and streams possibly, because we're all about, we need to get a lot of small data through it. Now, that's the usual too, of course, but we are using many experts, so the whole system needs to also be thought about that. There are some interesting optimization and papers about optimizing gems for the experts and picking the experts and stuff. And because here, because you're only using, for example, 8 out of 256 or something, it can very much matter where in RAM now. There's the interesting ideas about, maybe coalescing them if there's a common group, or ordering, so that you can benefit from them, the cache, or reusing and stuff. It's all about placement. That's one thing I'm trying to say here. Where is the experts that are being used in memory, and if we can get them into a faster flow, there's a significant benefit there, because otherwise we're going out to HBM and we can't use our any of the cache at all. And then finally, of course, there's the KV cache. Here it's a lot about page locality. So if we're using things like GLM5, which have the what's the word? But picks the 2048 keys, then there's a big benefit possibly from actually optimizing for that, possibly using, for example, removing them so that the gather operation is fast and stuff like that. It's very much about locality, similar to the experts. You want the data to be in the fast part, but that might mean actually having an operation that moves it together so that the later operations are faster. But that's all just speculative, of course. So there's always a difference in what Hopper could do and Blackwell. And so this is just a kind of quick group of things that might have failed or not been worth trying on Hopper that probably are worth retrying on Blackwell. The first is, of course, quantization. It's no longer just about smaller memory. The fact that the hardware can consume it, the format, it's definitely worth looking at. If you can get the quality up with the thing, it's going to be a big boost. It's an interesting one here that Cutlass is, I read that is reporting that, again, this idea of grouping stuff for the decode with the experts can be a benefit, again, because of the change in the structure and the sizing of the data, because where it would have been too expensive, it now might fit because of bandwidth, where it's changed. Very much that persistent kernels and fusing is probably going to be more important, because the more we can spend, it's even more tuned in a way. HBM has become even further away than it was on Hopper. It was pretty far on Hopper, but now, because there's so many other little micro optimizations, and it really feels further away. The level T helps with that, but not it's still, fusion is going to help, particularly because we have more static RAM with TMEM, so we can do more double buffering and pipelining of the streams. KV cache, again, similarly, as we're moving from just let's throw all the keys and values at the system, and we're using things like fancy attention, non-linear attentions and stuff. Again, the sizing and the format is likely to become much more important, and the break-even point of where it's worth actually spending some time as we're creating the KV caches to where they go, or maybe reorganize it, is likely to become a bigger boost than it would have been Hopper. A little one here about the whole cross GPU stuff. That's something you sort of noted that, yeah, it's even further away. So now if you do have to send things like KV caches across due to tensor parallelism, it's going to get harder or it's going to hurt more because they're even slower. And the other interesting thing is, as I mentioned, there's some small improvements that I can't find very much information about really to the actual scheduler. Different cluster sizes, different orders and stuff, which are designed to better overlap work. And so there may be some interesting things there that where beforehand you couldn't get the right performance by trying to stream or overlap, but might be worth it now because they've actually tweaked the actual level of the stream itself. Pretty obvious thing, but just put these into presentations. Whereas, do we optimize? So the kernel stuff, yeah, great, but to a large extent, that may not be the game. This is something we've all seen, where you have a great performance increase, but it doesn't actually work at the wall time, because as you go up the stack, other things sort of take it just doesn't make enough, change the mark enough. So while it's interesting to do kernel optimizations, and there's certainly we need to do it, and that's clearly something we need to think, again, because the actual architecture of Blackwell is more optimized to a certain flow, and you want to things like at the operator level, very much shape types, batching probably is a real, it was always a win, but it's like, this is a real win. If you can just get it fitting into TMEM and SMEM, you know, whereas beforehand it kind of worked okay, you've got a different set of parameters. So it's really worth doing those sweeps and optimizing for exact shapes and memory types. At the model level, similar prefill and decode. Prefill has such a different shape on Blackwell, if you can use, particularly if you're using quantization, but also because you desperately want to be able to get it into SMEM and TMEM and fit those numbers versus just the sort of straightforward, does it fit? It's like, does it fit, and does it have enough room for a second stream, or you know, the TMA to be pulling out and and swizzling as we go, and then obviously at the GPU level, similarly, sort of rules. So that's actually it, but I have a couple of low-level appendices just to go through because I think they're interesting, even if they're things. So this is the actual difference between desktop and data center. So shader model 10X, so Blackwell B200s are 100 and B300s are 103A. So they have 64 warts per shader model, whereas the desktop doesn't. It actually has fewer number of warts, only 48, and they're 120, by the way. They're all 120 at the moment. There's no odd one. I think GB10 is 120A, but that thing. As I mentioned, one of the biggest difference is in the actual static RAM. So desktop only has 128 kilobytes for its shared RAM, and no TMEM at all, because it doesn't have the Tensor Core 5s. It still uses WMA. So whereas the data center ones, they have their full 228 kilobytes of shared memory, and then the additional 256 kilobytes of tensor memory. So from a simple scaling point of view, they have way more fast RAM, almost double. Well, no, way over double, almost quadruple. So anytime you do play with the smaller the desktop type things, the actual sizes of any kernels are going to be like almost a quarter, even without the extra quantization hardware and so on. So it's just worth an interest in to know how far it is off when it comes to real sort of tensor work. In terms of normal CUDA cores and normal kernels, they're a lot closer. They do have basically the same CUDA units, but yeah, tensors, they're now effectively separate, which is interesting because that's also where AMD have gone. They have RDNA, which is their desktop ones, and they have a completely separate architecture called CDNA, which is done by their big boxes, their data center boxes, and they are now they're not really connected at all. I mean, they started for the same, but they've diverged so much, they're radically different. And I suspect we'll see more of that from the video going forward, that it's the data center stuff is so important, it doesn't make sense to actually keep it aligned to the desktops. The only thing that hurts is it would be lovely if we could actually put a small card in the PC or something, but yeah, AMD have moved towards allowing that. They're actually introducing one, but so far NVIDIA, there isn't a single way outside of a data center GPU that you can actually use the data center capabilities. So that's it. And this is this other appendix. This is actually what changed between the Blackwell 200 and the Blackwell 300. So from Blackwell to Blackwell Ultra. So 300 is 103A. And it's actually got some interesting little changes that I don't think have made it up to the higher level stuff yet, or not all of it. But the first is they support a whole bunch of extra block sizes for the matrix multiply. So beforehand, normal Blackwell only supports what's called block 4 mode, whereas Ultra supports a 16 and a 32 mode, which means it's actually there's more flexibility about how the blocks are arranged and whatever. They also similarly support a K equals 96 tile dimension. Normal Blackwell support power of 2, so 128, 64 to 128. Clearly, they found a case that was worth adding in hardware that is an intermediate, so 96, a non-power of 2. Again, probably trying to fit that shape exactly. Another thing that they've added to the tensor memory unit is the red unit, reducing load. So the TMA itself can do a reduction. Now, as far as I know, this hasn't made it up to Qt yet. It's still actually at the PTX level. And I haven't looked at it too closely, but you can now do the reduction, basically of dedicated hardware to do the reducing load without going into registers and doing it via CUDA unit. Again, probably a very specific, probably for softmax, they found that little bit of hardware here, and we can boost that. So that might be worth interesting looking at really low level, because this is B300 only. Probably the biggest change is they actually extended the access from CUDA units to TMEM. So the load store, well, just generally, but the load store unit has moved to 32 bytes. So they've doubled the peak load and store width from the CUDA cores, which is a pretty big change, because it means that the sizes you want to transfer now may be bigger when you're not using the TMA. It's worth it. I actually need to check. Maybe the TMA uses them as well. But yeah, it's just interesting that they've actually widened that, and that again is one of these clear things that they looked at the numbers, they profiled it, and said, hey, this is worth doing because that was a bottleneck somewhere. So that it's something that's worth looking at when we're doing transfers. If on a B300 we use slightly bigger and we get better numbers. And then the last one, it's actually related to the K equals 96, but they added to the TMA the swizzling modes for that 96 byte mode, so that it just matches it. So they can automatically swizzle into the ideal format. And one tiny little thing, which is kind of funny, because AMD have had this for like 20 years. It's been a part of their architecture for years, which is a 3-operand min-max instruction in the CUDA cores. And this is clearly because of softmax, that they found that you're doing a lot of min-max, so it's worth just extending the instruction to have, or add an instruction that can do a single instructor min-max. I would presume the compiler would use this for you at this point if it's thing, but it's one of these lovely little things. It's really nice when you're doing lots of mins and maxes, and yeah, they've added that for the Blackwell Ultras. And that's pretty much it. So there's not a lot of difference between the Ultras to the non-Ultras, but they're interesting. They're very clearly targeted at very small things that they've noticed that they could tune while they were doing the refresh with the bigger memory controller and things like that. So they just tuned a few things while they were there. And that is the presentation. Any questions?
That was great.
Okay. Yeah, it's and just generally looking around it, I personally find it quite interesting to look at these architectures at the lowest level, PTX kind of thing, because you can see the engineers, the hardware engineers' thought process. It's like they didn't just add that value there because they felt like it. Well, sometimes they do because they find that it's an easy to add, but most of the time, and having worked quite closely with them at Apple, it comes because the data, they've analyzed the data and they've said, you know what, that isn't that hard to do, and it just gives us that little thing. And so for refreshes like this, it's really nice to look at and I just did this as I got Claude to do a PTX diff, and just went through literally each instruction change and going which ones are interesting, because though it's a little bit, it does give you some nice little hints about sizes and things that just wouldn't work on a B200 if you didn't look at it. You wouldn't even know. It's because it's not mentioned. They don't even publish a list of what they've changed or anything. It's just it takes forever to actually build up through the hierarchy stack. And it is interesting that these may be focused on these because of the new Qtile, as I think it's called, thing which starts to do the tiling for you. You don't use an actual. So it could be that now they're starting to realize, well, wait a minute, if this isn't something that somebody has to think about using the K equals 96, but the optimizer automatically generates it, it's worth extending these with a few odd modes to help. Okay. If there's no more questions, I'd say this is done.
Thanks very much, Dean.